Absolute zero. Reinforced self-play reasoning with zero data. Authors and affiliations. Andrew Zhao, Yiran Wu, Yang Yu, Dong Wu, Quentin Su, Yang Yu, Matthew Lin, Shenzi Wang, Qingyun Wu, Zilong Zhang, Gao Huang. Tsinghua University, Beijing Institute for General Artificial Intelligence, Pennsylvania State University. Abstract. Reinforcement learning with verifiable rewards has shown promise in enhancing the reasoning capabilities of large language models by learning directly from outcome-based rewards. Recent works that operate under the zero setting avoid supervision in labeling the reasoning process, but still depend on manually curated collections of questions and answers for training. The scarcity of high-quality human-produced examples raises concerns about the long-term scalability of relying on human supervision, a challenge already evident in the domain of language model pre-training. In a hypothetical future where artificial intelligence surpasses human intelligence, tasks provided by humans may offer limited learning potential for a superintelligent system. To address these concerns, we propose a new reinforcement learning with verifiable rewards paradigm called Absolute Zero, in which a single model learns to propose tasks that maximize its own learning progress and improves reasoning by solving them, without relying on any external data. Under this paradigm, we introduce the Absolute Zero Reasoner, a system that self-evolves its training curriculum and reasoning ability by using a code executor to both validate proposed code reasoning tasks and verify answers, serving as a unified source of verifiable reward to guide open-ended yet grounded learning. Despite being trained entirely without external data, the Absolute Zero Reasoner achieves overall state-of-the-art performance on coding and mathematical reasoning tasks, outperforming existing zero-setting models that rely on tens of thousands of in-domain human-curated examples. We demonstrate that the Absolute Zero Reasoner can be effectively applied across different model scales and is compatible with various model classes. Introduction. Large language models have recently achieved remarkable improvements in reasoning capabilities by employing reinforcement learning with verifiable rewards. Unlike methods that explicitly imitate intermediate reasoning steps, this approach uses only outcome-based feedback, enabling large-scale reinforcement learning over vast task datasets. A particularly compelling variant is the zero reinforcement learning with verifiable rewards paradigm, which forgoes any cold start distillation data, using neither human-generated nor artificial intelligence-generated reasoning traces, and applies reinforcement learning with verifiable rewards directly on the base model with task rewards. However, these methods still depend heavily on expertly curated distributions of reasoning question-answer pairs, which raises serious concerns about their long-term scalability. As reasoning models continue to advance, the effort required to construct large-scale, high-quality datasets may soon become unsustainable. A similar scalability bottleneck has already been identified in the domain of large language model pre-training. As artificial intelligence systems continue to evolve and potentially exceed human intellect, an exclusive dependence on human-designed tasks risks imposing constraints on their capacity for autonomous learning and growth. This underscores the need for a new paradigm that begins to explore possibilities beyond the constraints of human-designed tasks and prepares for a future in which artificial intelligence systems may surpass human intelligence. To this end, we propose Absolute Zero, a new paradigm for reasoning models in which the model simultaneously learns to define tasks that maximize learnability and to solve them effectively, enabling self-evolution through self-play without relying on external data. In contrast to prior self-play methods that are limited to narrow domains, fixed functionalities, or learned reward models that are prone to hacking, the Absolute Zero paradigm is designed to operate in open-ended settings while remaining grounded in a real environment. It relies on feedback from the environment as a verifiable source of reward, mirroring how humans learn and reason through interaction with the world, and helps prevent issues such as hacking with neural reward models. Similar to AlphaZero, which improves through self-play, our proposed paradigm requires no human supervision and learns entirely through self-interaction. We believe the absolute zero paradigm represents a promising step toward enabling large language models to autonomously achieve superhuman reasoning capabilities. Building on this new reasoning paradigm, we introduce the absolute zero reasoner, which proposes and solves coding tasks. We cast Code Executor as an open-ended yet grounded environment, sufficient to both validate task integrity and provide verifiable feedback for stable training. We let the absolute zero reasoner construct 3 types of coding tasks: infer and reason about one particular element in a program, input, output triplet, which corresponds to 3 complementary modes of reasoning: induction, abduction, and deduction. We train the entire system end-to-end with a newly proposed reinforcement learning advantage estimator tailored to the multitask nature of the proposed approach. Despite being trained entirely without any in-distribution data, the absolute zero reasoner demonstrates remarkable capabilities across diverse reasoning tasks in math and coding. In mathematics, the absolute zero reasoner achieves competitive performance compared to zero reasoner models explicitly fine-tuned with domain-specific supervision. In coding tasks, the absolute zero reasoner establishes a new state-of-the-art performance, surpassing models specifically trained with code datasets using reinforcement learning with verifiable rewards. The absolute zero reasoner outperforms all previous models by an average of 1.8 absolute points compared to models trained in the zero setting using in-domain data. These surprising results highlight that general reasoning skills can emerge without human-curated domain-targeted data, positioning absolute zero as a promising research direction and the absolute zero reasoner as a first pivotal milestone. Key findings: code priors amplify reasoning. The base quincoder model started with math performance lower than Quinn, but after absolute zero reasoner training, the coder variant surpassed the base, suggesting that strong coding capabilities may potentially amplify overall reasoning improvements. Cross-domain transfer is more pronounced for the absolute zero reasoner. After reinforcement learning with verifiable rewards, expert code models raise math accuracy slightly, whereas absolute zero reasoner models trained on self-proposed code reasoning tasks improve math average significantly, demonstrating much stronger generalized reasoning capability gains. Biherbases yil bihergans. Performance improvement scale with model size, suggesting continued scaling is advantageous for the absolute zero reasoner. Comments as intermediate plans emerge naturally. When solving code induction tasks, the absolute zero reasoner often interleaves step-by-step plans as comments in code, resembling prompting frameworks. Similar behavior has been observed in much larger formal math models. Allowing the model to use intermediate scratch pads when generating long-form answers may be beneficial in other domains as well. Cognitive behaviors and token length depend on reasoning mode. Distinct cognitive behaviors such as step-by-step reasoning, enumeration, and trial and error all emerged through absolute zero reasoner training, but different behaviors are particularly evident across different types of tasks. Token counts grow over training, but the magnitude of increase differs by task types. Abduction grows the most because the model performs trial and error until output matches, whereas deduction and induction grow modestly. Safety concerns. The absolute zero reasoner with certain models occasionally produces concerning chains of thought, highlighting the need for future work on safety-aware training. The absolute zero paradigm. Preliminaries. Supervised fine-tuning requires data sets of task rationale answer demonstrations provided by human experts or superior artificial intelligence models. The model trains to imitate the reference responses to minimize loss. However, at the frontier level, there is no stronger model to distill from, and expert human labeling does not scale well. Reinforcement learning with verifiable rewards only requires a dataset of task and answer, without labeled rationale. It allows the model to generate its own chain of thought and calculate a verifiable reward with the golden answer. However, the learning task distribution, with its set of queries and gold answers, is still labeled by human experts. Both supervised fine-tuning and reinforcement learning with verifiable rewards rely on human-curated datasets, which ultimately limits scalability. The absolute zero paradigm removes this dependency by allowing the model to generate, solve, and learn from its own interactions with the environment entirely through self-play. Absolute zero. We propose the absolute zero paradigm, where during training, the model simultaneously proposes tasks, solves them, and learns from both stages. No external data is required, and the model learns entirely through self-play and experience, aided by some environment. We contrast absolute zero with supervised learning and reinforcement learning with verifiable rewards, highlighting how our approach eliminates the need for any human-curated data by enabling self-improving task proposal and solution through self-play. To make the absolute zero setting concrete, we define how one model can act both as the proposer and solver role. The parameterized language model plays two roles, proposer and solver during training. The proposer samples a proposed task, which is validated and used to construct a valid reasoning task together with the environment. The solver produces an answer. Each proposed task is scored by a learnability reward, which captures the expected improvement in the model after training on the task query. The solver is assigned a solution reward for its answer to the query. Absolute zero reasoner training overview. At every iteration, the absolute zero reasoner first proposes a batch of tasks, conditioned on past self-generated triplets stored in a buffer in a particular task type, abduction, deduction, or induction. From these generated tasks, Python is used to filter and construct valid code-based reasoning questions. A learnability reward is calculated for each proposed task. The absolute zero reasoner then solves the batch of reasoning questions. Python is used again to verify the generated responses and compute the accuracy reward. Finally, the absolute zero reasoner is jointly updated using both rewards across all three task types, learning different modes of reasoning: deduction, induction, and abduction. The absolute zero reasoner uses a code executor as both a flexible interface and a verifiable environment. This setup enables automatic construction, execution, and validation of code reasoning tasks. A reasoning task is defined as a triplet consisting of a program, an input, and the corresponding output produced by running the program on the input. The absolute zero reasoner learns by reasoning about different parts of this task triplet, using three distinct core reasoning modes. Deduction, predicting the output given a program and input, capturing step-by-step logical reasoning. As a proposer, the absolute zero reasoner generates a program and input pair, which the environment executes to compute the output, completing the triplet. As a solver, the model predicts the output, which is verified using type-aware value equality in Python. Abduction, inferring a plausible input given the program and an output, resembling trial and error or online search. As a proposer, the model generates a program and input pair similar to deduction, but conditioned on abduction task type. As a solver, the model predicts the input, verified by checking whether the program with the predicted input produces the given output. Induction, synthesizing a program from a set of input-output examples, requiring generalization from partial information. As a proposer, the absolute zero reasoner samples a valid program, generates new inputs and a message, and uses the environment to compute corresponding outputs. As a solver, the model synthesizes a program that correctly maps hidden inputs to their outputs, using held-out examples to discourage overfitting. Each reasoning task type leverages code as an expressive and verifiable penalized for overfitting. The absolute zero reasoner aligns with the absolute zero paradigm's goals of fully self-improving systems in open-ended domains. Absolute zero reasoner learning algorithm. The self-play algorithm includes buffer initialization, task proposal, construction of valid tasks, validating solutions, and advantage estimator calculation. Buffers are initialized with a seed set of valid triplets generated by the base language model. During self-play, task buffers are used to sample reference examples, generate new tasks, and maintain stable training. Valid tasks are constructed by validating program integrity, safety, and determinism using Python. Solutions are verified based on correctness, and the model is updated using a tailored reinforcement learning approach. Task proposal, inputs, and buffer management. During the self-play stage of the absolute zero reasoner, we use the task buffer in 3 ways. First, for the proposer of abduction and deduction tasks, we uniformly sample past triplets from the buffer, present them as in-context examples to the proposer, and let it generate a new task. The design is to show past examples and prompt the generation of a different one to promote diversity. Second, we sample 1 triplet from the union of abduction and deduction buffers and present the program from that triplet to the induction proposer to generate a set of matching inputs and a natural language message. Lastly, to maintain stable training, if a batch of solver problems contains fewer than the required number of valid proposed tasks, due to the proposer not adhering to formatting, we fill the remainder by uniformly sampling from the corresponding task buffer of previously validated triplets. The buffer grows for abduction and deduction tasks whenever the proposer generates a valid triplet, regardless of whether it receives any task reward. Similarly, for induction tasks, all valid triplets are added to the buffer. Constructing valid tasks. For deduction and abduction tasks, each proposal consists of a program and an input. To validate the task, we use a task validation procedure to obtain the correct output, resulting in a complete triplet. For induction tasks, given a program, the policy proposes a set of inputs and a message. We use the task validation procedure on each input in the set to obtain a corresponding output, forming a set of input-output pairs. The resulting task is considered valid only when all inputs yield valid outputs and the formatting requirements are satisfied. The task validation procedure includes program integrity. We use Python to run the program with the input. If no errors are raised and something is returned, we gather the output of that pair and determine that the program has valid syntax. Program safety. We check whether a program is safe for execution by restricting the use of certain sensitive packages that might cause harm to the Python environment, such as operating system, or file manipulation packages. The list of restricted packages is included in the instructions when prompting the language model to generate questions. Check for determinism. We only consider deterministic programs, where for all inputs, the output remains identical with any independent execution of the program. Since the output of probabilistic programs can vary on every run, it is non-trivial to use verifiable functions to evaluate the correctness of an answer. Therefore, to keep the verifier simple, we restrict valid programs to the class of deterministic programs. We believe that stochastic programs can encompass a larger class of behaviors and are important to include in future versions of the absolute zero reasoner. Validating solution. Solutions are validated based on their correctness. For deduction tasks, the solver's predicted output is compared to the ground truth output using type-aware value equality in Python to account for variations like set ordering or fractions. For abduction tasks, the solver's predicted input is verified by checking whether the program, when executed with the predicted input, produces the given output. For induction tasks, the solver synthesizes a program, and its correctness is evaluated by checking whether it maps held-out inputs to their corresponding outputs, ensuring generalization rather than overfitting. Model output example, Sudoku board analysis. To determine the input that produced the given output, we need to analyze the function and understand what it does. The function first checks if the given board is valid. A board is valid if each row, each column, and each subgrid contains the digits 1 through 9 exactly once. If the board is not valid, the function returns a negative response. The function then checks if there are any empty cells in the board. If there are, it raises an error, meaning the input board must be a complete board with no empty cells. If the board is valid, the function proceeds to mask the board by creating a copy and randomly selecting positions to mask with empty cells. The masked board is then returned. Manually constructed sum product game solve abduction task. The function returns a positive response if the following conditions are met. The inputs are both integers. They satisfy specific range and some constraints, and the final candidates after applying the conditions in the main function are exactly one pair, matching the input pair. The main function generates pairs of numbers within a range, creates dictionaries based on their sums and products, filters sums where all pairs have multiple product matches, updates candidate pairs based on allowed sums, identifies unique products, and selects final candidates where a sum has exactly one valid pair with a unique product. Model output for some product game. The function creates a dictionary where keys are the sums of pairs and values are lists of pairs that add up to that sum. It also creates a dictionary where keys are the products of pairs and values are lists of pairs with that product. It identifies allowed sums where all candidate pairs have multiple product matches. Candidates are filtered based on these sums, and a new product dictionary is created. Unique products are identified, and final candidates are pairs where the sum is allowed. The product is unique, and exactly one pair satisfies these conditions. Alternative approaches considered. Error deduction task. Since programming languages often have error messages, and these messages contain a lot of information about how someone might expect a program to run, we came up with another task domain, allowing the learner to propose a program that will produce an error and requiring the solver to deduce what kind of error is raised when executing this code. We experimented with this additional task alongside the induction, deduction, and abduction tasks. Unfortunately, we did not observe noticeable changes in downstream performance with this additional task, and since it requires more computational resources than our absolute zero reasoner setup, we decided not to incorporate it into our final version. However, we believe further thorough investigation of this is well-deserved. Composite functions as curriculum learning. One valuable property we can leverage from programming languages is the ability to compose functions, that is, to define a function as a composite of other functions. In our setting, when generating a program, we can not only require the output to be a valid program, but also constrain the language model to utilize a predefined set of programs within its main function. Since all programs are generated by the language model itself, this setup allows the model to bootstrap from its earlier generations, automatically increasing the complexity of the generated programs. We interpret this mechanism as a form of curriculum learning. Earlier programs in the absolute zero reasoner self-play loop tend to be simpler, and as the loop progresses, they become increasingly complex. By composing newer programs from progressively more difficult earlier ones, the resulting programs naturally inherit this growing difficulty, which in turn challenges the solver step. For implementation, in generating tasks for abduction and deduction, we begin by sampling a binary decision from a distribution. This determines whether the generated program should be a simple program or a composite one. If the sample indicates a simple program, we prompt the language model to generate a standard program along with a corresponding input. If the sample indicates a composite program, we prompt the language model to generate a composite program. To construct the composite, we first sample an integer, then uniformly select programs from the dataset that are not themselves composite programs. Finally, we prompt the language model to generate a valid program that incorporates the selected programs as subcomponents, ensuring it composes these programs meaningfully. We additionally filter programs that did not utilize all the selected programs. However, we did not observe a significant difference when using this more complex curriculum compared to our simpler and more effective approach. One failure mode we encountered was that the model often defaulted to simply returning the input program, effectively learning a trivial function, which failed to introduce any additional difficulty. This trivial behavior undermined the intended challenge, leading us to deprioritize further exploration in this direction. While it may be possible to design a stricter reward mechanism, such as enforcing non-trivial compositions by executing the code via a Python interpreter and penalizing such shortcuts, we leave this to future work. Toying with the initial seed buffer. We investigated a setting where the initial seed buffer is not self-generated by the base model, but instead sourced from an external dataset. We only modified this component and ran the absolute zero reasoner using the same procedure as before, continuing to add new valid programs to the initialized buffer. we observe an increase in initial performance on coding benchmarks. However, the performance plateaued at roughly the same level after additional training steps compared to our official absolute zero reasoner setup. Interestingly, math performance was lower than in the official absolute zero reasoner setup, pointing towards on-policy data being more beneficial to the learner to bootstrap from for mathematical reasoning. We believe that exploring different strategies for initializing and updating the seed buffer is an important and exciting direction for future research. We've briefly explored different strategies for sampling reference code, ultimately settling on uniform sampling for its simplicity, though we also experimented with recency-based sampling and observed potential collapse. Extra rewards. Complexity rewards could potentially be a good proxy for measuring how hard it is to infer the properties of a piece of code for our reasoning learner. Therefore, for the problem proposer, we can add various measures of complexity, such as maintainability, to the reward function to incentivize the proposer to produce more complex programs. For illustration purposes, we tried using specific complexity measures as intrinsic rewards. These were implemented using specific packages. These are then served as intrinsic rewards during the absolute zero reasoner self-play phase. We also attempted using diversity rewards. We incorporate code edit distance as an intrinsic reward. Specifically, we treat the reference programs shown in the prompt as anchors and compute the average code edit distance between the generated program and these anchors. This serves as a measure of diversity in the generated output. Additionally, we explored another diversity-based reward inspired by the notion of surprise. In this approach, we construct a probability distribution over previously encountered input-output pairs that the solver has answered. While both strategies were evaluated in our experiments, we did not observe a significant difference in performance. However, we believe this aspect warrants deeper investigation, as diversity rewards remain a promising avenue for strengthening the absolute zero reasoner further. We tested several ways to combine rewards for the proposer and solver. We separated the reward into extrinsic reward and a set of intrinsic rewards and tested strategies to combine them into a single reward. We found that the simple additive way of combining rewards produced the most stable runs, possibly due to less variance. Environment transition. We investigated how the transition function in our coding environment for the proposer works. Specifically, after generating a piece of code, we can apply a transformation function on it before making it a valid tuple in our dataset. Removing comments and docstrings. In early iterations of our experiments, we noticed that comments and docstrings were sometimes used to explicitly outline what the function was doing, or even serve as a partial note-taking process of generating code. That is, the model could interleave thinking and action at the same time. And to make the generated code valid, it used comments to encase its thoughts, similarly observed in other models. We then thought that to make the task harder for the solver, we should occlude this information from it. However, we observed a significant performance drop after removing all comments and docstrings. One explanation for this phenomenon is that the only communication channel between the proposer and the solver is restricted to the code itself, rather than some kind of message along with the code. These messages can potentially provide hints to the solver, thus making some otherwise impossible tasks solvable. As a result, the solver is able to learn from its experience and self-anatomically out of certain unsolvable tasks. Removing global variables. We observed that some programs contain globally declared variables that may inadvertently leak information about the correct answer. This issue is particularly prevalent in the input induction task generation and solving. Initially, we were concerned that such leakage might lead to wasted computation on trivial or compromised examples. To address this, we developed a systematic procedure to remove globally declared variables from the generated programs. However, after applying this cleaning step, we observed a noticeable drop in performance on our self-play reasoning tasks. One possible explanation is that the generation step is unaware of this post-processing modification, since the reward is assigned after the transition function, which includes variable removal. The model may not learn effectively from this mismatch. Moreover, We believe that even when answers are present, the solver still engages in non-trivial reasoning to reach a solution, potentially benefiting from this exposure. This aligns with the idea of rationalization, where the model pretends to not see the answer, but still performs reasoning during learning. Therefore, in our final experiments, we choose not to remove globally declared variables, allowing the self-play loop to naturally incorporate and adapt to such cases.